Finding the speed of sound. Using a tuning fork of known frequency as shown, we can hold it above a tube inside a container of water. The surface of the water acts as the sealed end of the tube. Slowly raise the tube until the volume of the sound increases. This is when the column of air has the same natural frequency as that of the tuning fork. The lowest point this happens at will be the fundamental frequency, which we can represent like this, with a displacement node at the water surface and a displacement antinode near the open end of the tube. Notice that the antinode is a small distance beyond the open end of the tube. Now we can measure this length, which I'll call L1, and we'll also make a note of the distance from the end of the tube to the antinode, which we'll call C for the end correction. As this is a quarter of the wavelength, we can say that lambda over 4, a quarter of the wavelength, is equal to L1 plus the end correction C. Now we continue to raise the tube until the volume rises again. This will be the first harmonic, which I can represent like this, again with the displacement antinode some distance from the end of the tube, a node here and a node at the water surface. Again we can mark this length, which now I'll call L2, and we also have the end correction C. Here we have 3/4 of a complete wave, so we can say that 3 lambda over 4, or 3/4 of the wavelength, is equal to L2 plus the end correction C. So now we have two expressions, both containing lambda and containing measurements L1 and L2, which we know. If we take this expression from this expression, we're left with lambda over 2 is equal to L2 minus L1. Note that the end correction C has gone. Now we know the wavelength and the frequency from the frequency of the tuning fork, so we can use the equation wave speed equals frequency times wavelength, or V equals F lambda, to find the speed of sound in air. Let's just run through a simple example. If the frequency of the tuning fork is 425 Hz, we've measured length 1 at 20 centimeters and length 2 at 60 centimeters. Find the speed of sound in air. Well, copying the final expression from before, that lambda over 2 is equal to L2 minus L1, we can write that lambda is equal to 2 times L2 minus L1. Putting the figures in, this means that the wavelength lambda is equal to 2 times 0.60 meters minus 0.20 meters, giving a wavelength of 0.80 meters. Then, using V equals F lambda, the frequency was 425 Hz. We've just found the wavelength at 0.80 meters, giving a speed of sound in air of 340 meters per second.